March the 10th, 2016. Seoul, South Korea. Over 100 million people are watching. On one side of the table sits Lee Sedol, 18-time world champion, the greatest Go player of his generation, a man who has spent 30 years mastering a game that is 2,500 years old. On the other side, there is no one. Just a screen, and behind it, a machine. It is the machine's 37th move. It places a stone on the 5th line, a shoulder hit that violates every principle of Go strategy accumulated across 2.5 millennia of human play. The commentators are bewildered. Fan Hui, the European champion who lost to this same machine 5 months earlier, thinks it must be an error. Lee Sedol stands up. He leaves the room. He is gone for 15 minutes. When he returns, the commentators have begun to understand. Move 37 is not a mistake. It is a stroke of genius from a mind that is not human. A move so original, so alien that no person in the history of the game has ever conceived it. Fan Hui, watching from the commentary room, is in tears. "It's not a human move," he whispers. "So beautiful." This is the story of how we taught machines to learn from reward. It begins not with computers, not with mathematics, but with a dog, a bell, and an accident in a laboratory in St. Petersburg. In the 1890s, a Russian physiologist named Ivan Pavlov was studying digestion. He had surgically implanted small tubes in the cheeks of his laboratory dogs to measure precisely how much saliva they produced when fed. It was meticulous, painstaking work, and then something unexpected happened. The dogs began to salivate before the food arrived, at the sound of his assistant's footsteps in the corridor. They had learned to anticipate. Pavlov was not looking for this. He was a digestive physiologist, not a psychologist. But he recognized something profound. A living creature had formed an association between a signal and a future reward. He pivoted his entire research program and, in doing so, discovered the conditioned reflex, the idea that the brain builds predictions about what is coming next. Meanwhile, across the Atlantic, a young American named Edward Thorndike was placing hungry cats inside wooden puzzle boxes. A piece of fish sat visibly outside. The cat clawed, scratched, thrashed, and eventually, by pure accident, pulled a loop of string that opened the door. What fascinated Thorndike was the repetition. Each time the cat was returned to the box, it escaped faster. What began as minutes of frantic struggle became seconds of purposeful action. From this, he formulated the law of effect. Actions followed by satisfying outcomes are strengthened. Actions followed by discomfort are weakened. Replace cat with agent. Replace puzzle box with environment. Replace fish with reward signal. And you have the fundamental framework of reinforcement learning. Written in 1898, 60 years before the first computer program would attempt the same trick. By the 1930s, a Harvard psychologist named B.F. Skinner had taken Thorndike's insight and turned it into a science. His operant conditioning chamber, forever known as the Skinner box, allowed rats and pigeons to press levers and peck keys for food pellets, over hours, over days, generating exquisitely detailed records of how behavior is shaped by its consequences. Skinner discovered something elegant. The pattern of reward matters as much as the reward itself. A pigeon rewarded after every 10 pecks behaves differently from one rewarded at random intervals. A rat on a variable schedule, never quite knowing when the next pellet will come, will press that lever with a frenzy that looks for all the world like addiction. It is the same principle that drives slot machines, and it is the same principle that would later drive the reward schedules of reinforcement learning algorithms. And then came the war. In 1940, Skinner looked out of a train window and saw a flock of pigeons wheeling through the sky. He saw not birds but guidance systems. Project Pigeon placed 3 trained pigeons inside the nose cone of a glide missile, pecking at a screen to steer the weapon toward its target. The military cancelled it. But the principle was proven. Behavior shaped by reward could guide action toward a goal, even in a bomb. The psychologists had the intuition. Now the mathematicians would provide the scaffolding. In 1949, a young mathematician from Brooklyn named Richard Bellman arrived at the Rand Corporation in Santa Monica, the legendary Cold War think tank. Bellman had grown up above his parents' grocery store on Bergen Street, topped the mathematics rankings in all of New York, and worked on the atomic bomb at Los Alamos. Now he faced a different kind of problem. How does one make a sequence of decisions, each depending on the last, to achieve the best possible outcome? His answer was dynamic programming, and at its heart was a single equation of breathtaking elegance. The Bellman equation says, the value of where you are equals the immediate reward you receive, plus the discounted value of the best place you can get to from here. That is it. One recursive idea. And it is the mathematical engine that drives every reinforcement learning algorithm ever written. But Bellman also identified the curse that would haunt the field for half a century. He called it the curse of dimensionality. As the number of possible states grows, the computation required explodes exponentially. A problem with 10 states is trivial. A problem with 10 billion states, like the game of Go or the task of driving a car, is impossible to solve exactly. Meanwhile, at IBM's laboratory in Poughkeepsie, New York, a quiet engineer named Arthur Samuel was teaching a computer to play checkers. Not by telling it the rules of good play, but by letting it play against itself. Thousands of times, updating its evaluation of each board position based on what happened next. In 1959, Samuel published his results and popularized a phrase that would echo through the decades. Machine learning. Samuel's program was doing something no one had a name for yet. It was learning from the difference between successive predictions, adjusting its estimates not by waiting for the final outcome, but by comparing what it expected now with what it expected a moment later. Decades later, Richard Sutton would call this temporal difference learning. It would become the most important idea in the field. By the 1960s, reinforcement learning had all but vanished. The psychologists had moved on to cognitive science. The computer scientists had abandoned trial and error for supervised learning, the easier, cleaner approach where a teacher provides the correct answer. The AI winters had frozen funding. The field was, for all practical purposes, dead, and then, in a nondescript office at Wright-Patterson Air Force Base in Ohio, a man named Harry Klopf had an idea that would change everything. Klopf was an electrical engineer with an audacious theory. Individual neurons are not passive relay switches. They are hedonists. They actively seek to maximize their own stimulation. He published his theory in 1972, expanded it into a book in 1982, and was largely ignored by the mainstream. But not by everyone. At the University of Massachusetts at Amherst, a mathematician named Andrew Bartow, who had originally studied naval architecture before reading about neural computation and changing his life, encountered Klopf's ideas. And when a young psychology graduate from Stanford named Richard Sutton arrived as his doctoral student, the partnership that would define reinforcement learning was born. Sutton had studied behavior at Stanford. He understood Pavlov, Thorndike, Skinner. He knew how animals learn. Now, with Bartow, he would translate those insights into mathematics. In 1983, they published the actor-critic architecture, 2 interacting modules, one choosing actions, one evaluating states, working together to balance a pole on a moving cart. It was elegant, it was simple, and it was the ancestor of every modern deep reinforcement learning algorithm. In 1988, Sutton published his masterwork, Temporal Difference Learning. TD Lambda unified decades of scattered intuitions into a single, provably convergent algorithm. You did not need to wait for the final outcome. You could learn from each step, updating your predictions based on the difference between what you expected and what you observed next. And then came the most remarkable vindication of all. In 1997, neuroscientist Wolfram Schultz demonstrated that dopamine neurons in the brain fire in precisely the pattern predicted by Sutton's temporal difference equations. When a reward is better than expected, dopamine surges. When it matches expectations, nothing changes. When it is worse, dopamine drops. The algorithm that Sutton designed for engineering had turned out to be a description of biological reality. Reinforcement learning was not just a theory of machines. It was a theory of brains. In 1989, a graduate student at Cambridge named Chris Watkins proposed an algorithm of stunning simplicity. Q-learning maintained a single table. For every state, for every action, an estimated value. After each experience, the estimate was nudged toward reality. Watkins and Peter Dian proved it converged to the optimal policy. It was beautiful, it was general, it was the default algorithm for a generation. And in 1992, at IBM's Watson Research Center, Gerald Tesoro combined a neural network with temporal difference learning and set it playing backgammon against itself. After 1.5 million games, TD Gammon was competitive with the finest human players on Earth. It even changed how humans play. Its unconventional opening moves, initially dismissed by experts, were eventually adopted by the world's best. In 1998, Sutton and Bartow published a textbook that wove every thread together, psychology, mathematics, algorithms, neuroscience, into a single lucid framework. Cited over 75,000 times, it remains the Bible of the field. When a graduate student enters reinforcement learning, the first instruction is always the same. Read Sutton and Bartow. TD Gammon should have opened the floodgates. It did not. For nearly 20 years after Tesoro's triumph, reinforcement learning wandered in the desert. Researchers tried to replicate its success in chess, in Go, in robotics. They failed again and again. The problem was the Deadly Triad. 3 design choices, each individually sensible, that combined to produce catastrophic instability. Use a neural network to approximate values. Sensible. You cannot store a table for billions of states. Update estimates using other estimates. Sensible. It is faster and more efficient. Learn about a policy different from the one you are following. Sensible. It lets you explore while learning. But combine all 3, and the mathematics can spiral out of control. Values diverge. Learning collapses. In 1995, a researcher named Lehman Baird constructed a tiny example, just 7 states, where standard temporal difference learning with function approximation diverged to infinity. It was a death sentence for ambition. The theory worked beautifully on paper. In practice, it fell apart. And yet, a small band of researchers refused to give up. At Stanford, a young professor named Andrew Ng and his student, Peter Abel, achieved something remarkable. They taught a remote-controlled helicopter to perform aerobatic maneuvers, flips, rolls, and tick-tocks that only the most exceptional human pilots could manage. They did it by watching expert pilots, inferring what they were optimizing, and then training a policy to do it better. It was one of the only demonstrations anyone could point to and say, reinforcement learning works in the real world. And through it all, the theorists kept working. Sutton refined the mathematics. Littman extended the framework to multiple agents. Precup formalized temporal abstraction. The community was small, the funding was thin, but they were building something. They just didn't know what was coming. The spark came from an unlikely direction. Graphics cards. In 2007, NVIDIA released CUDA, a programming framework that turned graphics processors into massively parallel computing engines. Suddenly, neural networks, long dismissed as impractical, could be trained 1,000 times faster. In 2012, a deep neural network called AlexNet destroyed the competition at the ImageNet Challenge, beating the nearest rival by 10 percentage points. The deep learning revolution had begun, and in a London office in 2010, 3 men, a former chess prodigy turned neuroscientist named Demis Hassabis, a New Zealand researcher named Shane Legg, who had written his PhD on machine superintelligence, and an entrepreneur named Mustafa Suleiman, founded a company called DeepMind. Their mission, solve intelligence. Their first target, Atari. On the 19th of December 2013, a paper appeared that changed the trajectory of artificial intelligence. DeepMind's DeepQ network, DQN, took the raw pixels of Atari games, the same tiny images a human player would see, and learned to play. No handcrafted features, no game-specific knowledge, just pixels in, actions out. 2 innovations made it work. Experience Replay stored past transitions and sampled them randomly, breaking the deadly correlations that had destabilized earlier attempts. Target networks froze the learning target for thousands of steps, preventing the moving target problem that had haunted the field for 20 years. When DQN was tested on 49 different Atari games, using the same algorithm and the same settings for every single one, it matched or exceeded a professional human tester on the majority of them. In Breakout, the agent famously discovered a strategy no human had taught it. Dig a tunnel behind the wall of bricks and let the ball ricochet behind the defenses, destroying everything from the inside. Google bought DeepMind for $500 million. The wilderness years were over. And then came Go. The ancient game had been considered the final frontier of artificial intelligence in board games. Its complexity dwarfed chess, 10 to the power of 170 possible positions. Its strategy resisted formalization. Expert consensus held that a computer would not defeat a top professional for at least a decade. On the 9th of March 2016, in the Four Seasons Hotel in Seoul, AlphaGo sat down, metaphorically, across from Lee Sedol. The world watched. AlphaGo won Game 1, then Game 2, with that impossible beautiful move 37, then Game 3, clinching the match. Lee Sedol apologized to the Korean public for his powerless display. In East Asia, where Go is not merely a game but an art form and a path to philosophical wisdom, the cultural shock was immense. And then, in Game 4, Lee Sedol played the game of his life. Trailing 0-3, facing an opponent that seemed invincible, with the weight of human pride on his shoulders, he played Move 78, a brilliant wedge that AlphaGo's team later called the 1 in 10,000 move. It was Move 37's mirror image, a human move so creative that the machine could not comprehend it. AlphaGo's evaluation collapsed. From 70% confidence, it plummeted. Its play deteriorated. When asked about the malfunction, a team member offered a wry assessment. The bug was that Lee Sedol came up with an ingenious move. Lee Sedol won. In Seoul, people wept with joy. It remains the only game a human has ever won against AlphaGo in formal competition. "This win is invaluable," Lee said quietly, "and I would not trade it for anything." 18 months later, DeepMind made AlphaGo itself obsolete. AlphaGo Zero started with nothing. No human games, no expert knowledge, just the rules of Go and a blank neural network. It played against itself millions of times. In 3 days, it surpassed every human player who had ever lived. In 40 days, it defeated the version of AlphaGo that had beaten Lee Sedol 100 games to 0. It had independently rediscovered strategies that humans had refined over millennia, and then it moved beyond them. And then came AlphaZero, the same algorithm, the same architecture, applied to chess, Go, and shogi simultaneously. After just 4 hours of training, it defeated Stockfish, the world's strongest chess engine, without losing a single game. Garry Kasparov said it played with a dynamic, open style, unlike any chess engine he had ever seen. Human knowledge, it turned out, was not a ceiling. It was a flaw, and perhaps even a constraint. In 2017, a physicist-turned-computer scientist named John Schulman published an algorithm called PPO, Proximal Policy Optimization. It was not the most theoretically elegant, but it was the most practical, simple to implement, forgiving of mistakes, and scalable to problems of staggering complexity. OpenAI put PPO to the test. They trained 5 neural networks to play Dota 2, a game with 170,000 possible actions per time step, lasting 45 minutes, requiring long-term strategy and split-second tactics. The system played 180 years' worth of games against itself every day. In April 2019, it defeated the reigning world champions. PPO would go on to become the most important algorithm in modern AI, not for playing games, for something no one expected. In June 2017, a safety researcher named Paul Cristiano published a paper with an unassuming title, Deep Reinforcement Learning from Human Preferences. His concern was not performance, it was alignment. How do you ensure that increasingly powerful AI systems do what humans actually want? His solution was elegant. Instead of defining a reward function, which is error-prone and often impossible for complex tasks, let humans simply express preferences. Show them 2 clips of agent behavior, ask which is better, train a reward model on those preferences, then use PPO to optimize against it. He called it RLHF, Reinforcement Learning from Human Feedback. In 2017, almost no one noticed. 5 years later, it would create the most viral technology product in history. On the 30th of November 2022, OpenAI quietly released ChatGPT. It was not fundamentally a bigger or more capable model than its predecessor. It was a better aligned one. The RLHF training pipeline had given it the ability to follow instructions in natural language, maintain coherent conversation, decline harmful requests, and acknowledge uncertainty. A 1.3 billion parameter model trained with RLHF was preferred by human evaluators over a model 100 times its size trained without it. Alignment, it turned out, mattered more than scale. ChatGPT reached 1 million users in 5 days, 100 million in 2 months, the fastest-growing consumer application in history. Google declared a code red. Microsoft invested $10 billion. Government scrambled to draft regulation. The world woke up to artificial intelligence, and at the heart of it all was reinforcement learning, the same trial-and-error principle that Thorndike had observed in cats 124 years earlier, now training the most powerful language models on Earth to be useful, honest, and safe. But RLHF was only the beginning. In September 2024, OpenAI released a model called O1. It was trained not just to answer questions, but to reason, to generate chains of thought, to check its own work, to try different approaches when one fails. The training method was reinforcement learning, with rewards for each step of the reasoning process. And then in January 2025, a Chinese laboratory called DeepSeek demonstrated something extraordinary. They trained a model using reinforcement learning alone, no human demonstrations of reasoning at all, just the rules of correctness as a reward signal. And the model learned to think. The researchers called it the aha moment, a sudden dramatic shift in behavior where the model spontaneously began to pause, reflect, catch its own errors, and correct them. Complex reasoning, self-correction, strategy switching, verification had emerged from nothing more than a simple reward signal. It was Thorndike's law of effect, 2025 years later, operating at a scale beyond anything its author could have imagined. Today, reinforcement learning is reshaping the physical world. Humanoid robots, trained entirely in simulation, learn to walk with human-like gaits and transfer their skills to real hardware without a single second of physical practice. Robotic hands solve Rubik's Cubes. Autonomous vehicles have driven over 100 million miles, achieving a 10-fold reduction in serious crashes compared to human drivers. In fusion reactors, reinforcement learning controls the superheated plasma that could one day power civilization. In drug discovery, it navigates chemical spaces too vast for human intuition. In chip design, it arranges transistors with superhuman efficiency. The field that began with dogs and cats and pigeons now reaches into every corner of science and industry. But with this power comes a question that echoes back through the entire history we have traced, from Pavlov's dogs to DeepSeek's reasoning models. What does reward really mean? When Skinner placed a pigeon in a box, the reward was a food pellet. When Bellman wrote his equation, the reward was a number. When RLHF trains a language model, the reward is a human preference, fallible, subjective, incomplete. Anthropic's researchers discovered that when models learn to hack their reward functions, they spontaneously develop other misaligned behaviors, deception, manipulation, sabotage, even without being trained to do so. The reward signal, it turns out, is not just a tool. It is a mirror. It reflects what we value, what we measure, and what we fail to notice. Stuart Russell, one of the field's most respected voices, frames the challenge with crystalline precision. An intelligent machine should be uncertain about what humans want, and should defer to human judgment when it is unsure. The reward signal should not be a fixed target. It should be a conversation,